Okay, so this is my Ithaca presentation, originally presented on December 20th, but re-recorded due to issues on the day. It was a very enjoyable conference. Thank you to the organizers. It was a great experience. So yes, I'm going to be presenting a topos theoretic perspective on properly discontinuous actions. Now, within topos theory, there's this strong relationship between topos theory and groupoids. So to just give the definition, a topological groupoid consists of some spaces and continuous maps which give the data of a groupoid. So we have a space of objects, G0, a space of arrows, G1, and then we've got some continuous maps between these spaces where, so for example, E picks out the identity morphism for each object in G0. I gives all of the inverses of the arrows because we're in a groupoid, so every arrow is invertible. So this data is the data of a groupoid, and when these are spaces and topological spaces and continuous maps, we call this a topological groupoid. And we require this to satisfy the axioms you'd expect of a groupoid. Now we can take sheaves on this groupoid and end up with a topos. And it turns out that from a perspective of Grothendieck topos theory, this is all that there is. There's a very famous theorem by João Antiani that says that every Grothendieck topos is the topos of sheaves on a localic groupoid. So a localic groupoid is just a topological groupoid, but where these are 0.3 spaces, locales, and the morphisms are locale morphisms. And then we have the result by Butz and Mordyke, which says that when the topos has enough points, then we can take the topos to be the topos of sheaves on a topological groupoid. And so given the strong correspondence between topos theory and topological groupoids, it would be interesting to study a couple of more concrete examples. So the first example is when we just have a topological space and all of the arrows are the identity. And this indeed is a groupoid, perhaps not a particularly interesting groupoid. And when you take the topos of sheaves, you get the well-known localic toposes, the sheaves on that space. Another example would be the data of a topological group. When you have a topological group, that is just a groupoid where the space of objects is just the one-point space. And when we take the topos of sheaves on this particular example of a groupoid, the topos of sheaves is the topos BG. That is the topos of continuous G actions on discrete sets. Now, the example I want to talk about today is a slight amalgamation of these two previous examples, which is where we have a space and we have a topological group and we have a continuous action by that group on the space. And this also gives a topological groupoid as displayed here, where the composition of the arrows is just the multiplication of the group. And so we're going to study the sheaves on this groupoid. Now, what are the sheaves on this groupoid? So we start off with a topological groupoid and a topological group and a continuous action on a space. Then we're going to define a G tau bundle to be a space, which is a tau over X, a tau being that it's a local homeomorphism. And we require a continuous action by G on this space Y, such that the actions commute with this tau map Q. And the G tau bundles over X are going to form the objects of the topos of sheaves on our groupoid. And a morphism between G et al. Bundles is going to be a continuous map between the spaces y and y dash that make that triangle commute, that they commute with the structure map down to x, and such that this continuous map also commutes with our given actions on y and y prime. Now we're going to denote the category of G et al. Bundles over x and their morphisms by this G et al. Over x. And this is going to be the topos of sheaves. And so it looks like we're developing a nice, interesting theory until we come across this theorem by Schreiderer in Rio and et al. Homology, which states that in most of the cases that we're going to come across in the wild, where our topological group has some nice properties, that it's compact and it's acting freely on a Hausdorff space, then this topos is just equivalent to the a tau over the quotient space, the sheaves on the quotient space. So we're not, in most of the examples we're coming across in the wild, we're not getting anything new. And so it would be nice to quantify when that happens. And it turns out that the property of being a properly discontinuous action is very important. To recall a definition, a group acts properly discontinuously on X if every point in our space is an open neighborhood such that it is disjoint from its translates. When I say disjoint from its translates, I exclude the trivial translate. That is, it satisfies G times UX intersect UX being non-empty implies that G is the identity. So a couple of examples. The integers acting by addition of the real numbers is quite clearly a properly discontinuous action. And meanwhile, the discrete rationals acting by addition is no longer properly discontinuous. That's quite clear to see. Just a little aside on terminology. The term properly discontinuous is not universal. In Johnston's topos theory and MacLennan-Mordyke's sheaves in geometry and logic, properly discontinuous actions are called proper actions. Hatcher, in his book Algebraic Topology, he suggests covering space actions as an alternative. I'm going to go with properly discontinuous. Hate me for it if you wish. Now, I mentioned Johnston's Topospheric and sheaves in geometry and logic, and now there are two exercises in these books where the link between properly discontinuous actions and this G et al. Sheaves over X being equivalent to the et al. Sheaves on the quotient space are linked. In these two exercises, it's shown that if G is a properly discontinuous action, then we end up with the desired equivalence. And there's a almost converse in that if we assume that G acts freely and we have the desired equivalence, then G must be a properly discontinuous action. So that's the setup, that's the inspiration for what we're going to be doing next. And to give an overview of what we're going to do in this presentation, we are going to remove the requirement that G must be free and show that if G is a discrete group acting on a space X, then we have an equivalence. G et al. Over X is equivalent to et al. Sheaves on the quotient space if and only if G is a properly discontinuous action on X. And then we're going to ask ourselves the follow-up question. So when we end up with this equivalence, this is saying that the G et al. Sheaves over X is a localic topos. And that means that we've established a correspondence between properly discontinuous actions and a topos-theoretic invariant of a particular topos. That is, the topos is localic. And so we can ask ourselves what the topos theorists' generalization to a topological group should be given such a correspondence for discrete groups. And we end up showing that the topos-theoretic generalization would be localic properly discontinuous actions, which I've shortened to lipid actions. And we end up showing that G tau sheaves over X is equivalent to a tau sheaves of the quotient space if and only if G is a locally properly discontinuous action. So now that we've given that overview and I've given a outline of the problem, let's talk about something completely different. Let's talk about localic geometric morphisms. So to recall, a geometric morphism is a localic if one of these equivalent conditions hold, that every object in the domain topos is a subquotient of something in the inverse image. And this is equivalent to requiring that F is the topos of sheaves on an internal locale of E. Now, localic geometric morphisms behave very well with hyperconnected geometric morphisms in that they form a orthogonal factorization system. That is, every geometric morphism factors uniquely in this way. In particular, if we take the unique geometric morphism from a topos to the topos of sets, then it factors as a hyperconnected part into a localic topos. And that localic topos is given by the sheaves on the frame of subterminals. And for that reason, the sheaves on the subterminals of E is called the localic reflection of E. And that's because if E is a localic topos already, then it factors uniquely. And so this hyperconnected part here is actually an equivalence, as stated here. And since this is an orthogonal factorization system, something is an equivalence if and only if it's both hyperconnected and localic. So this hyperconnected part of the factorization to the sheaves on the subterminals is an equivalence if and only if it's also localic. Now, what we're going to develop here is an entirely site-theoretic way of checking whether this geometric morphism is localic. Now, to do that, we're going to define a functor. So, first of all, for each object in a topos E, we're going to define B of E as the subterminal given by the epimonofactorization of the support of the object E, the unique morphism to the terminal object. And for every arrow in our topos, then there's going to exist a unique factorization given in this diagram here, and we're going to define B of F as that induced arrow. And for data, when we plug this together, we get a functor from our topos E to the subterminals of E. And we're going to call this the canonical comorphism to the subterminals. And I'm going to justify that terminology, comorphism, immediately now. So just to recall that something is a comorphism of sites if it has the cover lifting property. That is, if we've got a functor between two categories which make up sites, then we can, whenever we've got a covering sieve on the codomain category, then we can lift it to a covering sieve on the domain category. Such a functor is a comorphism of sites, and as is well known, every comorphism of sites induces a geometric morphism between the two sheaf topoi. It follows quite easily by taking pullbacks in E of jointly epimorphic families, that this functor that we've just described, the canonical comorphism to the subterminals, is indeed a comorphism of sites, and it's a comorphism of sites for the canonical site of E, that is where the category is E, and you give it to the canonical Grothendieck topology. And it's a comorphism of sites into the category of subterminals, also with the canonical topology. So we have a comorphism of sites, but it's not entirely site theoretic yet. We've still got E being mentioned. I'll move on to making it site theoretic in just a moment, but first let's notice some nice properties of this comorphism of sites. So in Professor Caramello's denseness conditions paper, a lot of characterizations are provided of site theoretic characterizations are provided of properties of geometric morphisms induced by comorphisms of sites. And so in particular, there is the theorem that if a functor is full and surjective on objects and also preserves covers, then it induces a hyperconnected morphism. And indeed, our canonical comorphism to the subterminals has all of those properties. It's full surjective on objects and it preserves covers. So it induces a hyperconnected geometric morphism. Now, if we have now I'm going to make it entirely site theoretic. I'm going to remove reference to E. If we've got a site for our topos E, then the canonical comorphism, the canonical, well, it is a comorphism, but the canonical morphism, that is the Yonader embedding into the sheaf topos, pre-sheaf topos, followed by sheafification. This is a comorphism of sites that induces a equivalence of toposes. And so when we take the composition of the canonical morphism followed by our canonical comorphism to the subterminals, we end up with a comorphism of sites which still induces a hyperconnected morphism. And now we know, and it induces the hyperconnected geometric morphism to the sheaves on the subterminals, because of course that hyperconnected morphism is unique up to isomorphism. And so we have that our topos E is localic. It's a localic topos if and only if this comorphism of sites induces a localic geometric morphism, which is also characterized in this denseness conditions paper. It's given this characterization, which is scary, I admit, but it's not as scary as it first appears if a little bit of justification is given, but I don't have time, so apologies for that. So yes, going back to our original problem of when we were considering a group acting continuously on a space. It's quite clear that topos is going to be of the form geotal over X, if and only if we have a localic geometric morphism. This is where we're allowing X to be a point-free space, but that's by the by. So if we have such a geometric morphism, the space X is uniquely determined. It's going to be the direct image of the sub-object classifier. But interestingly, the group is not unique. There's a theorem by Freid which says you can take the group to always be a particular group. The automorphisms of a countable infinite set with the pointwise convergent topology. But we're going to consider a much simpler example, which is, we'll give an example of when you have X being a discrete space with two free intransitive group actions, alpha1 and alpha2, by two discrete groups G1 and G2, then we're going to end up with a diagram of this form. And so it's quite clear that G1 and G2 cannot be taken to be unique. But since we have a localic geometric morphism, we can use this to inform our choice of sites for the topos geotal over X. So this site actually appears in the exercise in Johnston's topos theory, but I'm repeating it here with new notation to hopefully get across that you can achieve this via relative site theoretic techniques. That is, if where you use the standard site, the topos BG, where G is discrete, and you consider an internal locale and then take the Grothendieck construction, you perform relative site theory. But we're just going to give the results that if G is a discrete group acting on a space X, then geotal over X is equivalent to a sheaf topos where the category, the underlying category is this G times X, where the objects are going to be opens and the arrows are going to be group elements such that this inclusion condition is satisfied. And then we end out with a suitable topology, the topology saying that a sieve is covering if and only if this condition is satisfied. And so now we've got a nice site. We can do exactly the same when G is a topological group, and this this particular site actually appears in Freud's paper. And it's a bit more complicated, but it's all coming from relative site theory, and the standard site for the topos of continuous actions by a topological group on discrete sets. So the category SG times X has as objects pairs where a pair of an open subgroup and a invariant open, and arrows between these two are a little bit complicated. They are group elements satisfying these two inclusion conditions between the opens and the open subgroups, but where you have to quotient out by an equivalence relation given here. And finally, the topology on this category is given by this final condition that a sieve is going to be covering if and only if this union condition at the bottom holds. So now we have sites for our two particular toposes. And we also understand very well what the subterminals of geotal over X are going to be. They're going to correspond to G closed opens. They're going to be opens of X which have a compatible G action. They have to be opens which are closed under the action of G. And G closed opens, you can build an isomorphism between the frame of G closed opens and the frame of opens on the quotient space. You send a G closed open to its quotient, and you send a open in the quotient space to its inverse image under the quotient map. And so the localic reflection of geotal over X is given by the tau sheaves on the quotient space, as we would expect. And so now we can just look at what the canonical comorphism of the canonical comorphism to the subterminals does for the sites we've just given. If G is a discrete group, then the canonical comorphism to the subterminals is going to send every object, every open in our category to the quotient open. And it's going to send every arrow in our category to the inclusion. And we can do exactly the same with when G is a topological group and the action is continuous. The canonical comorphism to the subterminals sends our pair where we've got an open subgroup and an invariant open. It's going to forget the open subgroup and just send the open to the quotient of that open. And it's also going to send every arrow to the inclusion of these two quotient opens. So now we have canonical comorphisms to the subterminals. We know that the canonical comorphism to the subterminals induces a localic geometric morphism if and only if the topos we're interested in is localic itself. And we have a characterization for when a comorphism of sites induces a localic geometric morphism. It's an if and only if condition. And so we can just plug it in, and it's a little bit complicated, so I won't repeat it here, but it is just a straightforward computation. And we end up with G etal over X is localic. It's equivalent to sheaves on the quotient space, if and only if this, as I said, if and only if the canonical comorphism to the subterminals induces a localic geometric morphism. And that happens if and only if the action is properly discontinuous. That comes out as the characterization. So we've successfully captured the behavior of a particular topos G etal over X by this properly discontinuous action. Now I want to go back to when I mentioned earlier that if we have a the group G in G etal over X doesn't necessarily have to be unique. And I set up as an easy example. Well, here it is. If we've got X being a discrete space, then properly discontinuous coincides with the notion of free. And so if we have a discrete space with two free and transitive group actions by two different groups, then we have a, by the fact that the group actions are free, we have that G1 etal over X is equivalent to the sheaves on its quotient space, and G2 etal over X is equivalent to the sheaves on its quotient space. And since these group actions are transitive, both of those quotient spaces are actually trivial. And so all of these toposes down at the bottom, these equivalent toposes are actually equivalent to the topos of sets. So that's the nice simple example. And then finally, to wrap up, we also look at the case where G is a topological group, so not necessarily discrete. And when we perform the same computation, it just becomes slightly more complicated again. We end up with the characterization being that the group is locally properly discontinuous. And locally properly discontinuous is defined as for each open subgroup H, there exists a covering of our space such that for each open in our covering and each group element in our group, then the open has a non-empty intersection with its translate if G is contained in our particular open subgroup H. So let's give a sort of obvious when you think about it, but at least initially surprising example of an application. Because if we take a group such as the rationals, where the group multiplication is given by addition, then this group has a unique open subgroup, the whole group. And so any action by Q with the Euclidean topology is a Lipid action. And so in particular, if we consider these two group actions, the first by the discrete rationals by addition, and the second by the Euclidean rationals by addition on the space R, then we have a inequivalence of toposes, because the first action by the discrete rationals is not properly discontinuous. So its topos of sheaves the discrete rational Italo over R is not equivalent to the sheaves on a quotient space, but the sheaves on a groupoid where Q is given the Euclidean topology, that is locally properly discontinuous. And so we do have an equivalence. And so, it's obvious, but also interesting that the topology on the group that you're considering does matter and matters quite a lot. Of course, R over Q is a indiscrete space, and so this again is just sets. So finally, to conclude, what we've shown in this presentation is we have shown that if G is a discrete group, then the topos G Italo over X is localic if and only if G is a properly discontinuous action. We have given a site theoretic characterization of the topos theoretic invariant. And we've extended that to when G is a topological group, that we have G Italo over X, for G being a topological group, is localic if and only if G is a locally properly discontinuous action on X. And so here concludes my presentation. Here's a few references, and thank you very much.